Hey everyone, and welcome to the class. A few things you want to cover is we're going to be shifting gears towards doing a project a little more rigorously based on stuff that you've learned and practiced over the last few assignments. And I did receive the dataset suggestions, so because I had asked for us to be able to find some initial datasets that we might want to narrow down on. From my first look, from what I saw, you picked reasonable data sets. So let's go over what you have, and then we can narrow down on one particular data set from there, and then we can get into our usual lesson. Any other questions or comments you have right now? Okay, so I'm sharing my screen. So this is from, let's see, it's from Kamal. Yeah. So your choice of data set. So let's see your 4 or 5. You have the primary tutor, 217. The acid signals. So the biological data set, cancer, Wisconsin. Okay. Let's see. So the first one, I'm thinking if it's only categorical, you might want to skip it.
Okay.
Everything is categorical. Yes, everything is categorical. So let's skip it for the first.
Hey, can you guys be a little louder? I think we're missing.
Yes. So yeah, and then when we go to the other ones, let's see what is the mix in here. Okay, the task associated here is not regression or classification, although you could use for that. So I think this one we could skip as well. Yes, this is seems ideal in some ways. The classification problem, this is pretty a popular data set. It's interesting that data set is a little imbalanced. So you see there's more instances in group 1 class than the other. So that'll Yes, so that'll give you room for how to handle imbalanced data set, because sometimes, I mean, in most cases when you have a highly imbalanced data set where one class has a much larger number of instances, then the algorithm gets biased if you're not correcting for it towards just by chance predicting any record as group 1 with a greater probability than other groups. So if I had a data set, like a cartoon data set with 99% of rows in group 1 and only 1% in other groups, then just by chance the algorithm will start predicting everything as group 1. So there is something we can do as part of the pipeline to control for that imbalance. So that's a good thing. And it's a good thing it also has missing values. A lot of real life data sets, industry, academia, whatever, has a lot of missing entries. So it's really good to learn how to handle that. So this seems ideal for now. Let's see the other data set too. Also, one thing you might want to do just before starting, if we do pick this project, is to just count how many entries are missing. You can use like a which statement in R and just count like which of your input data is equal to a space or whatever it is. Whatever is being used to encode the missing value when you open the file and see it if it's a question mark. If it's NA, you can always do something like which of these dot NA input data. And
sure.
You can also count the length of it to get the count. Because you don't just want to know where the input missing data is, but you want to know how many, those kind of things. So that just to make sure, because you have 699 by 10, so 6,990 entries in your matrix. So I'm trying to see what percentage of that is missing. Is it very much missing? Or like how bad the situation is. Okay, and then the other data set, I like the size of it. It's not too small, not too big, but still it's big enough to give you some headache if you're just running on your laptop for the first time.
Yeah.
So it's definitely very real life data set. So data set for sensorless drive diagnosis data set. So classification problem. Okay, so the drive has intact and defective components that results in different conditions. I see. At 12 different operating conditions. Okay. You're using some probe and some oscilloscope, and you're getting some data, and you need to use that data to figure out and automatically classify when the defective stuff has happened and what those conditions are and stuff. Interesting. It's a very interesting data set. I'm kind of curious if this is. Let's see. Well, there is no header in the file, so yeah. Interesting. Yeah. You know, because you'll be doing a lot of experiments, maybe it's good to remember, you can remember this data set that you collected. I would suggest this one would be correct for you to learn a lot more of this data science aspects of it. And then in our second project, you can deal with, say, a larger data set, then you can probably use this or another one that you pick when you learn about a little more handling. Yeah. So the one, yeah. Cool. Let's do that.
Thank you.
Let's keep moving. So I have one from Manish Reddy. Okay.
Hey, hi Pranit. I selected a lot and then I narrowed down.
Okay, so let's start with the narrow down first.
Yeah.
Just from looking at it, I worked with this, and this already before, and this is a very popular data set, especially the Pima Indians.
Yeah.
Wholesale data, yeah. So I think you do have very good feasible data sets just from first look. Let's look at it.
Oh, you already have it in your local.
No, I was searching for some recent results I did with Pima, so I will show you when we get there. Okay. Yeah, the forest fires. Huh.
I went into the dataset directly. I've copied a wrong link, I guess.
Yes. Yeah, but this is what I'm looking for. Okay, so you don't have missing values.
Yeah.
You have a mix of numeric and categorical.
Yeah, both are there.
Yeah. Size. I worked with this data set. This is a reasonable data set, but this data set will give you little trouble in being able to predict with high accuracy because there's not too much that can be caught that easily.
Okay.
So it's a popular data set for sure. Is this a regression problem or a classification?
I think it's a combination. I think it's a classification problem, I guess.
No, I think, I mean, we can use it as that, but I think he's selling it as a, yeah, like I said, it's a difficult problem. I said, right? That's what he mentions here. This is a very difficult regression task.
Yeah.
So, yeah. Also, we used to test outlier detection with it. So, it is not clear how outliers are there. So, yeah, you do have an outlier. At least you will get an idea of how to handle outliers in this data set. But I know a lot of people, even I had a lot of trouble in improving my prediction accuracy with a lot of techniques on this data set. It's not that hard to catch the signal here. That will be only the discouraging thing to start with. The rest seems good. Let's see the other ones. You picked some good other data sets too. So go back to it. This is a marketing campaign. Yeah. Yeah. So these kind of problems are very common actually. They come up very often. Also things like loan prediction. Is the guy going to be a defaulter or is he going to pay his loans if you give him a loan? That kind of questions. Some people also shared them in interview discussions if you're applying to that kind of companies, like say Capital One or something like that.
Yeah, that's the only reason I picked this up so that I can get some touch.
Yes. Okay, so 45,000 classification, no missing values. Yeah, I mean, this is definitely a good data set for sure. The size this is not big data, but it might give you some headache in the beginning though, just because things are slow as you're trying to do your stuff.
Yeah.
Yeah. Okay, this one I would not recommend just by looking at, this is too small a data set.
Yeah.
Yeah, let's get this. Things won't be very significant. Like you'll have a lot of variability in your same error if you keep running different.
Yeah.
Let's get that. Pima Indians is a very good data set for sure. It has missing values, classification. It doesn't have categorical variables. I thought it had that as well.
No, I don't think.
It doesn't have categorical. Okay. interesting. Okay, and then there is also create a categorical variable out of this if we bin something into two groups. But let's not do that in first pass if we use this stuff. Okay. You know what? I would recommend this data set. It's a very well studied data set.
Sure. I think it has a decent amount of instances too.
Yeah, I mean it's not very big enough, but let's see what's your first one though. To find, yeah, this is 517. Oh, this is a little too big. So yeah, this is somewhere. Yeah, this is okay. This is reasonable. You may not do 5-fold. You can do 3-fold cross volume. But
Okay.
yeah, there is good signal to catch in this data set for sure, though. To some extent. So yeah.
Sure.
So basically, this is a group of Native Indians, Native American Indians.
Yeah.
And women.
So
yeah.
Yeah.
Have you read the story about it a little bit? Yeah.
Yeah, a little I read it. It's about the pregnant woman. And,
yes, and for some reason they're very prone to being diabetic. Almost everybody.
Yeah.
Of them, so they were studying their health parameters, trying to classify and understand. Okay.
I just wanted to keep it a little simple, and I thought let's go.
Sure, yeah. I actually did something a few weeks back.
Okay.
And then it was like a decision tree with the same data set.
And
yeah.
Wow. And Pranit, one more small question. This is a good data set, but I have one more thing like this. Cars data set, if you open the email on the top,
Yeah.
Cars data set, it's the third, that one, yeah.
Okay. I think I heard of this.
Yeah, that's also a very good data set. Yeah, I choose those two, but then
so car, auto MPG or the automobile? Oh, cars, this one. Cars.
Yeah.
Forest fires is a hard problem. Interesting. Okay, let's see. Close this. Okay. I will. Okay, let me look at it quickly. We have a bunch of many different kinds of cars, not a couple.
Yeah.
Then some.
Yeah, missing values too.
Yeah. It has missing values. Okay.
Yeah.
Not much though. Only 6 missing values in the data set.
Yeah.
Yeah.
It's a small data set too. 398.
Yes. But still as a proportion of 398, right? 6 is very small, right?
Yeah.
Like, yeah.
It's very small.
Right. Okay, let's see the variables. Yeah, okay, it's nice. Yeah. Now you're trying to classify what exactly? Let's see. What is your class attribute?
They're trying to. I mean, it's just a historical data, and they're trying to get the MPG.
Okay. This one?
Yep.
It's a regression, I guess.
Yeah, it's a regression problem.
Okay.
It's a small thing. I don't think we can take this.
Yeah, that's what I'm saying. This is about to say actually. So it's small here.
Yeah.
Okay.
I'll go with the Prima Indians data.
It's very interesting. This exactly has 768 instance and this has 768.
Yeah.
Anyway, yeah. Oh yeah. I could. No wonder. Okay. Yeah, I think of these seems like these smaller. So let's stick with this. This is a very good data set.
Sure.
Like just courses, like in university courses, a lot of people use this as a assignment data set as well.
Sure.
Okay, let's keep going. Okay, so we have something. Oh, Parkinson's is very popular. There are 2 Parkinson's data sets on ML. The concrete compressive strength is popular too. Is this that? Oh, it's not the compressive. Okay, let us see. Okay, so Thiru. So I would recommend, there is another Parkinson's data set. This is just 197 rows. It's too small. There is another.
Okay, Pranit. I found another one too, right?
Yeah, there is one to do with some speech score called UPDRS.
Right.
Yeah, telemonitoring, and then there is another speech one. So one of these two, yeah, this is a good data set, and this is such a good. It's not that big. That rate is better in some ways. So that rotation, yeah. Yeah, UPDRS, class information. Okay, this is very, very popular data sets. These two ones, the newer ones. Yeah, I would. Yeah, if you end up doing the Parkinson's data set, we will do this basically. Only thing, it doesn't have missing values. It's not a very easy data set to get reasonable accuracy, but it's not as hard as forest fires either. The story here is Parkinson's patients, there is a scale of measuring how severe the Parkinson's is. It's called the UPDRS scale. It's very popular apparently in the healthcare community. So you're looking at their speech, because the speech of Parkinson's people is kind of, they mumble, and it's not as good as...
Yeah, the stammer.
Yeah. So you want to predict based on just their speech processing related variables, processing their speech, on what do you think, where they are on the scale. Like, are they completely okay, or are they like mildly Parkinson's prone, or where are they? Or are they already Parkinson's patients? That is the story in both of these data sets. Coming from two different groups, basically. This is a more popular one, the one from Oxford. A lot of people have studied this. Okay, so let's keep that in mind. This is the smaller one. The other two, this is the issue. There are interesting stories to it, but it's too small data to do machine learning on. If you divide it into 5 folds, you only have 20 rows per folder. So yeah, you want to skip the smaller ones. On the concrete, there is another one from the concrete. This is really small. There is one called concrete compressive strength. That is again a popular data set. Compressive strength. This one, yeah. 1030 rows, no missing values. So this is a regression problem. So they're trying to look at some properties that they measure of concrete that is being manufactured, and they want to predict how strong it is going to be. So, question for you. Do you feel more inclined towards this domain in general, like something coming from healthcare, this kind of data set, or do you feel more inclined towards this, if there is any reason?
I think I would take Parkinson's, Praneeth.
Okay, yeah. So we can definitely stick to this one then. It's a regression problem. This one is interesting. So I know this is a more popular data set than this group. If you choose to do regression, then definitely do pick this one. If you choose to do classification, you can pick this one because it also comes with the class information. But then you need to drop the UPDRS column when you try to predict 29. These two are very correlated. Let's see variables in this one. Yeah, here there are two variables for predicting UPDRS. One is motor one is called total UPDRS. These two are very highly correlated. So you either choose one and drop the other. Either choose this and drop this, or the other one and drop this. And then that will become your response variable, basically. Yeah, let's stick to this one, the popular one, the 5875 from Oxford.
Yep. Okay, Praneeth.
Yes. So, did we discuss money deeps? Not yet, right? Yeah, we didn't. Okay. Forest fires. Oh, Facebook metrics. I had a previous student do it. Not sure if there's a metric. You can comment on them. Forest fire internet usage. Okay. All right, forest fires. This is a very hard problem, so I would discourage anyone to do this in their first project. It will be a lot of headache. It's very hard to predict the variable in here. Just as you can guess, right? It's hard to predict like something like an earthquake. Earthquake is even harder, but forest fires may be somewhat better, but it's still very hard to predict when a forest fire is going to happen. Just for those only, it becomes a very hard problem.
Yeah, there was a recent fire in California, Praneeth, like it was a very big problem. So
yes, I know it is a big problem. It costs millions of dollars for sure.
Yeah.
From your from a learning perspective, it's going to be troublesome to learn.
Sure.
Yeah. I think there was the other one. Yeah, so let's do this too. This is a regression problem. Number 19. This is a Facebook performance metrics of a renowned cosmetic brand Facebook page. So their goal is to do marketing and reach people and get some value out of it. So that's what this is doing. And here, comment volume data set. I am hearing some noise from. Yeah, okay, that's okay. We're talking to you. Okay, so the Facebook comment volume instance in the dataset contains features extracted from Facebook posts. The task associated with the data is to predict how many comments the post will receive. Yeah, this is what my student works with. Size might give you some headache. Here it's let's keep this in mind while we look at other ones. Yeah, sales transactions. Clustering, let's skip this one, especially its time series. We've not studied that yet in our course. We will in the future.
No, but I couldn't hear you, Pranit.
Oh, I see. So this one, I think that we would skip it for 2 reasons. We've not studied the time series analysis yet.
Okay.
And also, it's not a supervised learning. It's a clustering, so it's unsupervised. It's not regression classification, unless you want to convert it into that. So it's this one.
Sure.
So, this is an interesting data set. I usually discourage it for people who are taking the course for career-oriented purposes because something that seems a little more realistic is going to be more valuable for your resume than saying like I did something with tic-tac-toe, for industrial purposes. So yeah, from that perspective, it's a good data set for sure. There's an interesting problem going on here. So let's get this one. Okay, this one is interesting. Tech, okay. The data set contains general demographic information on internet users 97. Attributes, no missing that. I'm not sure what the task is because they not mentioned it. You just have some demographic information in 1997 there. Let's see, there is a survey from the it was survey basis users. What are we trying to do here? You look into anything by chance? The problem that is to be solved, is it prediction, classification, or we define our problem ourselves? Full details of this available here. I mean, 1997 is old, but I'm trying to see if this is a rich data set for learning. Connection speed. Okay, there is a, I mean, yeah, this is one of those data sets where we need to define our own problem or read papers and see what problem was defined. Not this one, the other one. So let's do that. So that brings you down to one of these Facebook data sets.
Like a comment?
Yes, there's a comment volume, then there is a metric data set. So my concern is it's a little bigger, but we can downsample it and only choose a smaller subset of the data set. You can use it. When you're in the software field, it's kind of in line with your resume anyway. Right? It's not effective. So, yeah, we can pick this data set.
Sure. Thank you.
Yeah, you can start with this, but it will give you some headache. Things will be slow, right? So we can downsample and choose 10,000 or something. But keep this in mind. It's a bit too small, though. Yeah. So yeah, let's do this. Okay. Cool. We've covered everybody's data set. We still have half of our time left. So any other questions, concerns before we move into course material? Good type of random forest last call.
Hey Prince, so we are going to work on this data set, like, I mean, what would be our approach, like dividing it with, yeah.
Good point. Yeah. So the aim is, since we picked our data sets, we want to apply SVM, random forests, and if possible, neural networks. We can split it into 2 projects or 1 project because neural networks would be interesting to keep it a separate project. So first project would be apply SVM and neural and random forests. We'll be covering random forests today, and the assignment today will be from random forests as well. So you can apply on this data set itself, the one that you picked, because it will kickstart your project-related work. We want to do cross-validation. SVM, the parameters are cost and gamma, so you want to do the whole process that we discussed in the last couple of weeks. And then for the random forest, you want to do, there's two other parameters. We're gonna talk about it because we've not completed the class today. So instead of cost and gamma, we'll have those. You want to tune for those. And then you want to come up with a table. I will write this as input-output requirements in the doc. I'll send you. But you want to have a table of two methods and the cross-validation error obtained at the best optimal parameters that you chose. So you can compare which method is doing better at its best possible combination, and then you pick that method as your final prediction method, basically. But in the beginning, because it's a project, we're going to do some other things before we even apply this stuff. So what I will do is, let's open a Google Drive doc. I will send access to all of you after the class. Okay, you're going to have some phases in your project. Let me also open something, say from here. This is some previous student elsewhere. Actually, is also some sort of current student. It's kind of finishing off. So if you see, we're going to have different phases, but I'm going to populate your documents as we go through it. It'll be, most of the document will be common, the approach to each of you, but it'll be kind of specific because each of the data set might have slightly different issues than the other one and different terminologies. So we're going to have different stages in your project. The first project stage obviously is going to be loading your data set and doing some pre-processing, right? So we're going to do that. You know how to read files and stuff, but you got to do it as part of the project. Load dataset / pre-processing, and we're gonna populate it as we go, as we keep going. And then we're gonna do next stage. So in pre-processing, before that, I would call this exploration first. And then let's do pre-processing here. So you first start with loading your data set, which is obviously required. And then in terms of exploration, you need to understand the data a little more, right? So check data types using class function, right? And you wanna, so that you know which one is being treated as string, which is character, which is numeric, categorical. And if something is not in line with what you think it should be, you can convert it, right? If there is some numeric variable that it is treating as soon as you read your data set as a character variable, you can convert it into as.numeric. You can coerce it to numeric. Then check percentage of missing values, if any. Check class imbalance. So that means count how many records of each class in your variable, if it is a classification problem. And then, so you will know what the situation of your data set is. You're getting comfortable. You're not doing anything about it. But once you identify these things, based on that, you will take some action in pre-processing. Some pre-processing actions will be regardless of what the situation here is. So you would do that. Let's see. Okay, then you want to do some summary statistics. So basically trying to get them of numeric variables. So you're trying to get how many, the mean, median, and how the spread is for each variable. So you can use the summary function. You cannot compute that for categorical, obviously. There's nothing like a mean of male or mean of female or mean of gender. And then also one thing that will be important is for categorical variables, count how many unique possibilities in each categorical variable. So for example, gender is very simple to deal with. It's male or female. There's only two unique possibilities. There may be something like, say, if you're in Amazon, if you're looking at product type or like product category, there's like textiles, and within textile, there's 100 kinds of textiles. There's electronics, so and so, right? Books with many genres. So your unique set of categorical variables within the product type itself could be maybe 100,000 or 1,000,000. You never know. So then it's a whole different problem. You cannot just handle it the way you would handle a gender or like some category variable with a handful of unique possibilities. So you want to get a feel for what the situation is. That's why you're exploring here. You're getting comfortable. So you want to get these counts. Okay, so let's keep it at that. You can do some plots, for regression especially. Regression plot, input column versus output variable, the response variable. And then you can look at and see, get a feel for what the relationship is. Is it linear? Is it totally random? It's hard to predict based on one column. Just see how the curvature looks like, how the plot looks like. Because you're in the end predicting this variable and looking at the relationship with respect to this variable. Although the bigger problem is you're using all variables to predict it, but you'll get a feel for which are easier and harder. Yes.
So while plotting, do you want to use all the values or just take a sample of the data set and plot it and see what kind of problem it is? I mean, generally not all the
unless you have a very large data set, there is no reason why not to plot all the values. So, but if you have a many set, so if you have like 10 columns, right, or 8 columns, like in some of your data set, you can plot each column versus the response, all the values, obviously. But if you have like a million records and if you have like 50,000 columns, you obviously do not want to generate 50,000 plots for one column each.
Okay, thank you.
So, yeah. So you do that. You can also look at so the summary statistics phase here. It will give you a lot of numbers, right? Mean is this much, deviation is much. It might be hard for the visual eye to look at it. So a better visual representation summary is by box plots. There's something called a box plot. So this is a box plot. It can be tons of box plots if you click something like this. So let's see this. I'm picking some random box plot. So every variable has its own box. This is the median or the mean would be the dot line, and you would know how the spread is. So this is a lot of variance, and then the mean is skewed towards this side. So it means the data is skewed, the distribution. It's not like Gaussian. So there is less data on the left side of the mean than towards the right side, right? So there are bigger values here, the smaller values, that kind of thing. And then these values are more probable than these values, for example. Here it is symmetric distribution. Both sets of the mean similar behavior in terms of the area under the curve. Then this has lesser standard variance among the data because it's not varying much around the mean, but these data has greater variance than these. So you will understand very quickly the visual summary statistics because you're looking at the same thing. There are some where you can add in even more info like this. So this is the median, this is the third quantile, this is the first quantile. Median, so what is a quantile or a quartile? So the median is 50% quartile. So there is the area under the curve, left side of the median is exactly equal to the right side of the median. That's the median. That is the definition of median in terms of 50% quartile. 50% quantile. There's something called quantile and quartile. So the median definition I gave is for quantile in terms of the area under the curve. So this is like how many standard deviations are you away. This is the max. Is the max value is so far off from the min value. This is the range completely, and you're dividing it in terms of the area under the curve. So you can get all these kind of informations and labels in your box plot, but still, just visually looking at it, it gives you a lot of information in terms of summaries. And you can get all the variables in a single plot. Still know which variable is what because you have a name below each box. So it'll be easier. You can get 2-3 variables in one plot if it's a line kind of a curve, but if you have too many, then you'll have too many colors and labels. It might be a little hard to really see what's going on. Okay, so this is something you want to do initially. And then we get to pre-processing, right? Here, I will populate this more and more as we get there. But for now, your first thing would be here. And then I'm giving pre-processing some more points because if you have more time, you can get to it. These things, although there are a lot of lines of data, it shouldn't take too long to do this. I'm not saying it's going to be done in 10 minutes, but it's not going to take days and days together either. So pre-processing, apply. Well, first you want to deal with missing values using imputation methods. So an imputation method is as follows. If you have a data set with some missing values in different places, an imputation technique tries to predict what that missing value would have been. What is it more likely to have been? So that you're trying to fill your missing values with a better guess instead of putting some random number in there that will skew your data set, the story that your data set is trying to tell. An intuitive way to think about it is if you had, I'm just drawing a diagram so I can use this. If you had data set like this, these are your rows, these are your columns. Usually you have more rows than columns, but this is a cartoon. So let's do this. Obviously you have more than 3 rows that I'm drawing here. You have a lot of rows. So if I said, say this was missing, when I gave you the data set and say this was missing, and then you have a lot more rows here, obviously, right? And then there's some missing situation there too. Now, in order to impute this value, you want to figure out what value should have been here so that you can fill it up with that. You don't want to fill whatever random number. You don't want to put 100,000 or 5,000 here just like that. So then you're going to make it even harder to get a better prediction. So what you do is this is particular variable. You know this particular variable is missing, so you identify which variable is missing for this row. So to impute this guy, what you do is you look at other rows in your data set. You have many rows in your data set, right? So what you do is you look at other rows in your data set and try to find some rows where the rest of the values that are not missing in the row that you're trying to impute. So this is what you're imputing. So this is the row you care about. This is your query row. So this is not missing, this is not missing, this is not missing. Out of these 4 columns, you want to find in your data set other rows where these 3 columns are as similar in value as to what entries you have here. So that you're trying to find some guy or some row that is very similar in behavior to this row, right? So this is describing the demographic of some Southeast Asian female working in Wall Street, long hours but getting a good salary, living in a good part of New York City. That is a different demographic from somebody else, right? So if you want to estimate what this variable would have been for her, you want to find similar women in a similar demographic. If this was a demographic data set, so you want to find similar variables where you do not have a missing value in this row. So this is already available, and so are the rest available as well. So you want to see how this row is similar to these rows the most, and once you get the most similar rows, you find some nearest neighbors, and then you take the average of just those rows of data set that you identified as being similar to this particular woman, to a lady, and then that average you can use as your estimate in here. Now, this is known as k nearest neighbor imputation because you're trying to find k nearest neighbors, and you're trying to impute the value or the missing value based on available values from your nearest neighbors. But there are more complicated techniques. This is a more intuitive technique to explain. There are more complicated techniques. There's one called soft impute. This was developed by the authors of a very popular machine learning and statistics textbook called The Elements of Statistical Learning. This package is from Stanford University and from the authors of that book for machine learning. This is a popular technique as well. So yeah, there are many techniques of varying levels of complexity, right? But you want to use at least k nearest neighbors, k-NN impute, to be able to. So k-NN impute, you don't need to implement it. There's k-NN imputation in R. There's many packages that do it. So you want to use that to deal with missing values. These are all real life situations that you would face when you deal with datasets in the future. There will be a lot of datasets that would really have missing values. Using it's like say k-NN impute or soft impute. And then do the deal with thing every time. So let's say categorical variables, apply dummy coding. So if you have we discussed dummy coding before? I guess not, right? So yes, so I will take that as a no. What I will do is you say, look, a simple example, if you have a gender variable, right, and possibilities are male, male, female, right, male, female, so and so. Now, this is one variable, the gender variable. Now, computers cannot understand this directly the way it is. You want to convert it into a numerical form. So what dummy coding does, dummy coding is also called one-hot encoding. Dummy coding, one-hot encoding, what it does is it takes this column and it splits it into two columns because you only have two unique possibilities. So now you have two columns. Now the question is what do you put in those? If you have male, you can say 1, 0. If you have male, again, 1, 0. If some row has female, then you would say 0, 1. Again, male 1, 0, female 0, 1, female 0, 1. So that's how you encode your data from this form to a numerical form that computers can do math with. The technique can work on this. If you pass this into the technique, it's going to break. Or it's going to do something wrong internally by coercing into some other form, which is not correct. The reason we're doing this, why are we not saying male is 10 and female is 50 or the other way around? Why are we not encoding with whatever code you want to encode with that is a number? That is because here, if you plot these 1001 on the number line, because we're working with numbers on the number line, right? So 10 is equidistant from the origin, 01 is equidistant from the origin. So both have a similar amount of bias you're giving. You're not biasing. So these are unbiased kind of representations. But if I say male is a very big number, female is a very small number, you're probably saying male is a very important variable than female for that prediction, or the other way around. So there is some inverse relationship. So you don't want to just encode into whatever numbers that will make you believe that one is more important than the other. Then you're biasing the technique towards the wrong direction. So here it's an unbiased way. 1001 are totally different. One is male, one is completely opposite to female in terms of the numeric representation. They're equidistant from the origin. This is called dummy coding. What would you do if you had like some variable that had high, medium, low for some other than gender, some other thing? You had three possibilities. Then you create three columns. Then you have 1, 0, 0, 0, 1, 0, 0, 0, 1 as the three unique possibilities. Now, do you have to write code to do this yourself? You can if you wish, but there are obviously functions that would do it much quicker for you. There is a dummy coding in caret library. There's a function, so it's like 1 or 2 lines of just calling that function, or dummy.code in psych. You can use one of those two options that are more popular. Dummy coding refers to one-hot encoding. The Python packages in scikit-learn usually call it one-hot encoding. The stat guys call it same thing. And so on and so forth. So you want to do this. Apply dummy coding only to categorical variables. So before you do that, you should be able to know which of your variables are categorical or which are numeric. You don't want to dummy code your numeric variables, or you don't want to leave any categorical variables without doing dummy coding. So only to categorical variables you apply this. Numeric variables by centering, scale, ZV and NZ. I will tell you what this is. Removal. Okay, now what I mean by this? There would be some variables if they have zero variance, which means the entire variable is completely constant in your data set. So it's basically a useless variable. You want to drop that variable because it's causing this unnecessary information being fed into your model. Because if everything is constant, I cannot predict anything based on that. If I tell you some column is always 100 in all rows, what extra information would I get in discriminating one particular row as being one class versus another class? If everything is 100, I have no clue whether it is one class or other class just by looking at that variable. So it's a useless variable that you don't want to use in part of your computations and your model. So you want to drop that. So it's called the zero variance removal. NZV means near zero variance. It's not exactly constant, but if I have 1,000 rows, 999 rows are constant. One row is a little different. So it doesn't really matter if it's a little different. If one row is very different, then maybe it matters. It's an outlier, maybe, you don't know. So if it's near zero variance, the variance of that column is very close to zero. So it's not varying at all. So it's nearly constant. So maybe it's only varying at a decimal point after 4 decimals. So it's the same as being constant, so you're going to remove it. Centering and scaling, you're just subtracting the mean of every column from itself. So you take the first column, subtract its mean from every row entry in that particular column. Then same thing, you subtract this column mean of second column from every entry in that second column. So basically you're centering every numeric variable. So you're doing this only to numeric variables. So you are making sure every variable is centered around the mean. Well, this is not the center, but yeah, something like this, right? And then maybe it could be skewed as well. So skew here, in this case, the mean would move somewhat this side, right? I should have drawn it the other way around, something like this. So the mean has moved towards the left than the peak because there's more data this side. So everything is centered at the same point, the center. So you're just moving, you're not changing the shape of your column. So each curve is a column, your variable. You're not changing the shape. You're able to perfectly compare them. They're centered around this. You're just translating the curve so that the mean is at the center origin, so that they're more comparable. Because now I know this is having more variance than this, and I know what the exact relationships are and stuff in terms of its distance from the center. That's what it's doing. Scaling is doing similar operation in terms of variance. It's putting everything on the same scale. So the range of your values, the sum of your values would always be 1. That kind of so you do this. So there's some pre-processing. If you don't have categorical, you can skip this. If you don't have missing values, you can skip this. But this thing, as long as you have numeric variables, you have to apply this. So that's what I meant. Some things, depending on what you observed in your initial stage and the extent of the situation there, you do this. Now, deal with class imbalance. Here, like I said, if most of your rows are coming from only one class and the other class very few rows, your technique is going to be very biased towards just randomly filtering that class, whatever you feed it in the future as part of your test data. So you don't want to do that. You want to deal with the imbalance in a reasonably better way. So a popular technique is called apply smoke. So what this does is, if you had a data set with imbalance, right? 90% of your rows are in class 1, 10% in class 2, then, and if you had 1,000 rows to start with, both these classes, what the smoke technique does is it kind of expands and exploits your data set from 1,000 rows to maybe 10,000 rows. It makes it a much bigger data set, but then it samples in such a way that in the 10,000 row data set, you would have class labels that are more balanced. Instead of 90-10, maybe it's 60-40 imbalance, which is much better. You don't need to have like exact 50-50 balance. It's going to be okay. It should not be very skewed like 90-10 though. So that's what smoke does. And then you would also have your random forest assignment. So let's have you do at least this and keep going as more you can in terms of pre-processing, but also you will finish your random forest assignment, hopefully, that I will give you. Any questions? And then we will keep expanding this. You will have exactly about 5 stages. So you can think of each as one stage. So you have 5 things to do, and then you'll be done with your project. Okay, so that's, for example, to get a feel for what you're, I'll just give you the headlines here. So data, what next you would do, train test, right? Basically the splits. Then you would do initial model. Then you would do some model tuning. So this and this would be, because data subsetting is just 1 or 2 lines of code, an initial model where you apply some model, make sure it's working end to end, but you've not tuned your parameters properly. You just applied it. You make sure your code is running without error. Then you tune your initial model here, where you do validation, and then tuned model, and then you just select results / reporting, right? Basically, you can just call it reporting. Put them together basically in a report. MS Word doc or something. It's going to involve most of copy paste and writing some English around it, some language around it. So if you see, you have 5 stages of work, and then reporting is a separate part. Of course, it takes a little time, but it's not the same as solving the problem, doing the project. So we populated some for now. I will keep adding more and more as we go there, and looking at your progress, where you are, how you got stuck, and how much you covered successfully and stuff. Any other questions? Okay, so I will share this document with you all. Okay, I will share this after our call. So we have about 5 minutes. We can cover some amount of random forest. We covered half of it. As a recap, if you see, we looked at the overall structure of the technique. So here you're splitting your data set at a time and some threshold condition you take, and then you split whether you need to go into this split or this one, this set, what direction you're going to. And finally, after you apply all these conditions on one variable at a time at each level, at each node, you end up in the leaf node, which is your last node, where all you have is the class itself. So you're trying to predict gender using looking at computer vision cameras, looking at your images of people, and you want to predict gender. So it's a bad example. There's too many genders here. But anyway, what would happen is you would take different conditions, and then you would reach down, and then you will have either male or female in each of these leaf nodes. So based on what conditions of a row is satisfying, you will say to the male or female, or spam or no spam. So, so that's the overall structure. Now the question was, how do we make a split at each, based on any variable, right? How do you know what the split is, right? So let's look at that. The concept that is used is coming from information theory and a bit of statistics and probability as well. So there is a concept of information gain, which is defined as this equation, but this to be defined, you need to define what this H term is and what this is. These are simpler terms. The H term is called the entropy. We're going to define that and look into it as well. I'll give you some examples. Now this term, once you understand entropy and you understand, then you look at it, you'll understand why this is a good criteria to make a split and how it works. So I'm just pointing to what is what at this point. Now, these lines are just saying you're measuring the size of this set. So it's the cardinality. It's not the absolute value. So you're measuring the size of your set here, what is the size of set based on the split you've taken. So it's saying how much you're covering based on that split. So now we need to define entropy. That once you understand, then you will understand this quantity as to why it is useful. So entropy, the first definition of to start with the definition, it is just based on probability of your events. So you're looking at the probability times the log of that probability base 2, for example. So why is this useful? Let's look at it now carefully. This is the entropy part. Once you know this, you'll understand the information gain. So yeah, it comes from these areas, right? Coding theory, information theory, statistical physics, machine learning, etc. So let's give you an example. So entropy is basically a measure of uncertainty. So probability is some sort of a measure of how probable something is happening. So something that is low probability has a high entropy because it's more uncertainty, because you don't know what's going on. It depends on the distribution of probabilities, right? If the probabilities are all equally likely, then that's what I meant when I say low probability. To be precise, if you have 10 events and all 10 events are equally likely to occur, then it's very uncertain to predict which one will occur. But if there is some pattern in the probabilities of which one is occurring more commonly and stuff, then you know that the entropy is not that uncertain, it's lesser. Your entropy equal to, you can think of it in your mind as uncertainty. So yeah, this is the formula, probability weighted by the log of the probability base 2. So let's see, if you had some random variable that can take 8 possible states, right? But there is some probability that defines which state it takes, which you don't know, right? How many bits to transmit the state of X, right? So basically, if you compute 8 times log of probability, times the log of probability is what you're going to compute, right? So the probability is 8, and if they're equally likely, then 8, all states are equally likely is what it says. So 8 times 1 by 8 will be the probability, because n possibilities total. And then you're multiplying with respect to the probability. So that will give you, this is going to cancel out. So you get log 2 cube base 2, you'll get 3 bits. So you don't need to give me a lot of information. You don't need too much memory to describe this phenomena. All I need is only 3 bits because they're equally likely. If I understand the entropy of one guy, I know the entropy of the other guy as well. So there's another table that computes the same and will tell you how many bits are required based on the probability distribution. What does high entropy imply? This is what I'm saying. It's high uncertainty. It means it's kind of uniform distribution, right? Equally likely, kind of boring thing. Histogram would be flat, right? You don't know which one is more likely to happen. If it is low entropy, then it's like lesser uncertainty, so it's more interesting. From a predictive standpoint, your histogram would have a different set of probabilities or counts with respect to different possibilities. So you know which is more likely, which is less likely and stuff. Now there is just like conditional probability, there's conditional entropy. This is what is very useful in the split that we're going to make. So say you had this data set, right? Number of cylinders of the car and the MPG is in a good state or a bad state in terms of its performance, the miles per gallon that it's giving, mileage per gallon. So, so if I were to just look at the uncertainty with respect to just one variable, you see 1, 2, you have 4 goods and 4 bad. So both are equally likely, both good and bad classes. So it's really hard. There's high uncertainty. You don't know which is going to happen. But if we give you more information about the cylinders, so if you want to look at the entropy of Y, given that the cylinders is equal to 5 or equal to 8 or equal to 4, then what is the entropy, right? So if I give you that cylinders are 8, there's only one possibility that is there in your data set that it is bad. So then you're very uncertain that the only outcome is bad. So you have a deterministic guaranteed outcome. So that's where the entropy is 0. But if I say the cylinders are 5, then you use that formula, right? Then you can look at how many have 5, and then you multiply that with the probability of the log of that probability. So then you get some number. So you will know how so here the uncertainty is very high. You don't know because it seems to be equally likely if you look at 5. There is one bad and there is one good. So you don't know. If I tell you if it has 5 cylinders, we are at the highest level of uncertainty in saying whether it is bad or good because they're equally likely. This is the other way around. Here it is always bad, right? There's only one 8 with only one bad. So that's what this is showing. I hope this example gives you a little more info of what's going on. So information gain is basically you keep making your split based on this conditional probability entropy we defined here. So you take each variable at each node and you make a split at different node, and you will see basically the reduction in entropy without that split versus with that split. So this is the entropy originally without any split, and this is the entropy with the split. This difference as big as possible so that you're getting more information from an uncertain state to a more certain state. So this difference is why we are using to make your splits in this diagram. This is your stuff. Now, let's give you a quick example. If you had some data set of The Simpsons, I give you
Printing the question here.
Yeah.
So
yes.
This works better if we are splitting a node into tail nodes, right?
This works better if you're splitting. You said, can you repeat the question a little more? Or add in more info?
We are splitting a parent node into 2 child nodes.
That's right.
There is no rule that we need to split the node into just 2, right? We can split into 3 or 4.
Yep, you can. Generally speaking, for decision trees, you can. For the different kinds of techniques, yes.
Yes, sir. This hold good for those kind of scenarios as well?
Yeah, it would, because you're taking one particular condition that will take you to this node versus another condition that takes you to this node. The condition will be different. The variable is the same, right? So this is one particular variable you're picking, then you're having 4, whatever number of conditions. Here there is 6 conditions. Now you will measure for any given row, which condition, if used, will have give you the most information gain. Then that particular test row will take that path, because all test rows will not fall in the same condition.
Yeah.
Yep. So yeah, you're only measuring information gain, and you're just sorting out and taking maximum based on whatever condition you apply here. This is your condition basically.
So whichever probability has a best, the node will be split based on that.
Yes, exactly. So let me give you a very relevant example explaining to what I said. So the Simpsons data set, say the goal is to predict whether it's gender or not, but I will not tell you who the person is. I won't give you this photo and all that name. I will only give you their hair length, weight, and age. Okay. So if you say, like my example, say if you look at based on hair length, one condition could be hair length less than equal to 5, then take one particular path. If it is yes, then maybe, because men Simpsons do, but there is this little false positive. There is this little baby who also has a short hair, right? She's not grown up yet. So that's a false positive. But it's a realistic part of the model. You never have 100% prediction in this cartoon. Then women with greater than length greater than equal to 5 and end up here, right? There may be some guy. This guy is a false positive, right? Yeah, he has long hair basically. He has this different demographic and different mentality. And then there's this funny fellow, this clown ended up here for some reason. He has long hair in different ways. But otherwise, it's doing reasonably well. But this is just one condition, but I can have another condition saying hair length is greater than 5 and less than equal to 7. And then another condition saying hair length greater than equal to 7. Then I'll have 3 nodes instead of 2. And anyone will fall in one of those buckets based on what the possibility is. You can always restrict your tree to be binary splits. Then you're only finding one condition, but you want to find multiple conditions, you can find multiple conditions as well. Okay, so this is the story. The theory ends, and this is like a nice example you can look at. So we can also maybe look at this for another 5 minutes in our next call, but this should not take the entire call in the next call, like work through some example and stuff. But by the way, this is only giving you about how to make the split, but the random forest is you keep doing that right till the end. So you do a recursive split. You only choose the nodes that satisfy this condition and this condition, and only with those rows, so out of your 1,000 rows, maybe 200 rows satisfy until here. So only those 200 rows will be used in making further conditions. You won't use all the rows again once you get down to here. You're basically recursively reducing the data set and only recursively sending your subset you have at any given point back into your splitting method. So this is called recursive partitioning, basically. All right, so there we are. Yeah, let's see. So yeah. You'll be getting more and more busy now because you'll be starting your projects. So let's see how that goes. I will share this. I will share your assignment, etc. Your assignment will basically be just like SVM cost and gamma. Random forest has 2 parameters: the number of trees you want to grow, because in random forest you want to not do just one tree. It is an ensembling technique, right? You fit multiple learners, your multiple trees, and you take an average or some weighted vote of these trees to take your final decision. So you can build 100 trees of this kind, but each tree is only built on a subset of the data set because you're resampling your columns that you want to use. You only want to set like the subset of all of your columns each time for each tree. There's some variability in terms of what features you're using. And then you take the average decision or the final vote of these trees in terms of classification or average decision for regression tree. So one parameter, just like cost gamma for SVM, one parameter that is important in random forest is the number of trees you want to use, right? Do you want to use too many or less, too few, or how many? This decides whether you're underfitting or overfitting or optimally fitting. And then there is also the bag size of how much you want to subsample in terms of how many features you use, etc. So one thing though, in general, random forest the parameter tuning is very important, but it's not as sensitive as it is in terms of searching the right parameter with respect when you compare it with SVM. SVM usually in practice, this is not a theoretical statement, just in practice, like an observation. The cost and gamma is very sensitive. The performance is very sensitive to cost and gamma choice that you're making. Here it is important. If you use too many trees, then it doesn't matter if you use even more trees than that. But once you use the right amount of trees, you're okay. And it doesn't change, your performance doesn't change too much either. But it's still very important to cross-validate. No technique is good enough if you don't cross-validate your parameters. It's no longer machine learning at that point. Okay, so you have these slides. I think this was already shared in last lecture in your email, so you can work through it as well. Any other things, questions, concerns, or we can call it a day for now?
Pranit, this is something not related to this class. So Hemant has asked us to learn some other tool other than the machine learning that what we are learning now. So how about learning MongoDB a good choice, or?
Learning what technology you said? You said MongoDB? It kind of broke whatever you said. I got the overall context. Can you complete the sentence again?
MongoDBs.
Yeah. So MongoDB does add value. I cannot definitely say MongoDB is better or Cassandra is better or another one because there are so many of these technologies. Or DynamoDB, right? There's so many. But yeah, so this is more of a database technology. Having some of that will be very good on your resume. Even one technology would be fine on the database side of things. It's also good to have SQL, just vanilla SQL on your resume, and be like at least being able to write some group by statements and basic statements, aggregate queries, and also doing inner join, left join, right join, and all that, joins properly, and being able to do the with clause when you're writing subqueries, right? You can use the with clause. So these are a few things that people usually ask if they require some SQL background for whatever position they're interviewing. These two things are good to have in general for the skill set. Also, from a machine learning standpoint, there's this distributed situation, right? Distributed situation where in very big companies, not always, if you have too much data, there's a scalability issue. You cannot just run in R or Python in your production just like that. So people do distributed computing. So for that, what is very popular these days is Spark. So I know a lot of people with a lot of experience, a lot of things that still don't know these things like Spark and deep learning and stuff. So this is something even big companies are catching on to, but now there's still a lot of people who are reasonably good at it. So having some projects or data wrangling that you did with Spark would be useful. Spark has a machine learning library called MLlib. So if you can, now you know what cross-validation is, what the methodology is. If you can say, after you do, at some point, if you can do a project or some mini project that says, I did random forests using MLlib in Spark, right? Then you know a way of running random forests on millions or billions of records because it scales up very well. Because when you run it in the company, you would have a big cluster that you're running it on. Although for your assignment, you would make your own laptop as a cluster of some sort, but at least it would be the same code. So Spark is very popular, but the good thing is if you know R or Python, there is a interface into Spark where you can kind of shield yourself with most of the workings of Spark by using PySpark or RSpark. It's just an interface like it into another language or package. So there are some nice blog articles. If you just search for PySpark, RSpark, some example, nice working, simple examples that you can literally do in your computer within over a weekend or over a week or two. Or run through that example at least, and then before you can do your own thing. So these are the kinds of technologies. So some database technology is good to have, but even having SQL is sometimes good enough. But having some database technology like MongoDB and stuff will make it even definitely a lot more stronger, right? More the better. No one will deny that. But also having something like, if you're on the science side of things, having something like Spark is useful as well. Spark has its own disadvantages as well, but at least for scalability, for whatever it offers, it scales very well. Then there's another tool called H2O. It's easier to use, but it's not that popular as Spark for sure in terms of scaling up machine learning on millions of records. So you can run a classification model on large data, big data basically, that kind of thing. Anything else?
No, that should be all, Pranit. Thank you.
Hey, small question. Yes. Are we concentrating more on the integration part of these other tools with R, or do we, I mean, SQL I accept about the joins and all that stuff, but the other tools?
Yes. The thing is, there is a path you're taking, right? From a beginner to becoming intermediate to, in the future, you may be a little more advanced as you work through these things a lot better and understand stuff more. So there is two paths going on. It's kind of conflicting, I understand. One path is the data science path. So you're learning the methodologies, tuning, technique, and this and that. But then there is, in a production setting, you may not always face big data, right? There may be big companies where you're working a good job where you don't have to face big data situation day in and day out. Then you don't have to worry about it. But sometimes people do face it, and this is always good to have in the resume. So the thing is, you want to do a project vanilla style without doing any big data. You at least want to understand, which is what you started to do with your SVM assignment, and you'll be doing with your first project. But then obviously once you get a feel for handling this project and dealing missing values, all the pipeline of the project, then I would highly recommend that you be able to do the same thing or some amount of this pipeline using some of the big data technologies should be your next challenge. So do you want to start preparing for that now itself? You're welcome to do that, right? You can study things on Spark or MongoDB or whatever. But do you want to do it separately, one after another? It's up to you. But as far as this course content goes, we are solely focusing on the data science, not just the data engineering aspect, right? So there's a data science part. And since you're software developers, you can always learn more skill sets on the data engineering side one after another at your own pace.
Sure, thank you.
Cool. Any other questions, comments? Okay, so yeah, let's call it a day. You guys all of you have a good weekend. See ya next week. Bye-bye.